let us determine the diameter required for this water pipe. The reservoir is filled with water as shown. The pipe is fitted with elbow and a gate valve. When the gate valve is fully opened, the water will discharge at 0.475 cubic meter per second. We know the depth and the length of pipe. So we are designing pipe diameter for the given flow rate and the given length and height. Also, the pipe is made of galvanized iron. First of all, let us calculate average velocity, as the velocity through the pipe is same at all points, since the pipe has the same diameter throughout. Volume flow rate is velocity times area. Solving for velocity, we get velocity as function of diameter. To obtain a second equation relating velocity and diameter, the energy equation will be applied between point 1 and 2, with the gravitational datum through point 2. As there is no pump and turbine fitted, these terms cancel out. Pressure at both point 1 and point 2 is same, as they both are at atmospheric pressure, and they cancel out. Velocity at point 2 is very high compared to velocity at point 1, so you can assume zero velocity at point 1. When designing pipe, you must account for two types of losses. One is major head loss, and other is minor loss. We can calculate major loss using this equation. In addition to this, head losses also occur at pipe connections, such as bends, fittings, entrances, and transitions. These are called minor losses. The formula for calculating minor head losses. Look how the major head loss and minor head loss are related with the coefficient. Major loss related with Darcy friction factor, whereas minor loss is related with loss coefficient. For loss coefficient, design manuals often provide such data. In our cases, there are two elbows, and loss coefficient for each of them is 0.9, whereas the loss coefficient for fully open gate valve is 0.2. There is also minor head loss due to flush entrance, so don't forget about it. Summing up those total minor head loss for now, and the total head losses. Now solve these energy equation. Combine equation 1 and 2, by eliminating velocity, we will obtain. Now, if you assume laminar flow, then you can solve this equation by using the friction factor as. But for this case, our assumption of laminar flow will be wrong. Because after solving and getting the velocity and diameter, calculate Reynolds number. It will be greater than 2000, which proved that laminar flow is wrong, so it is turbulent flow. For turbulent flow, we need our Moody chart. So, first get the surface roughness for galvanized iron pipe from your data book. To avoid assuming a value of f, and then solving this fifth-order equation for d, it is easier to assume a value of d first, calculate f, and then verify this result using the Moody diagram. For example, if we assume diameter as 1 meter, we get f as 31.34, which is very huge, and do not lies in the range. The same goes for d equals 0.4 meter, so we need even less diameter. If we assume d equals 0.35 meter, then we get f in the range. Now using this diameter, solve for velocity to obtain Reynolds number, and also get relative pipe roughness. Therefore, from the Moody diagram with these values, we attain friction factor as. But it is not equal to our previous friction factor, so our assumption of diameter was again wrong. So for the next iteration, choose more smaller value of d, that gives an f smaller than before. If we choose diameter as 0.3 meter, then f will be. Now again solve for Reynolds number and relative pipe roughness. We get the friction factor as. With these new values from the Moody diagram, which is fairly close to the previous value obtained from the previous equation. Therefore, we will use diameter as 300 millimeters.